Teleportation will commence in 5 minutes. Do not leave any luggage unattended. Unattended luggage will be removed and destroyed. Attention, ladies and gentlemen. This is an announcement from Planet X31. Please take your seats. Teleportation will commence in 2 minutes.
Greetings, planet Earth, and welcome to the Science and Cocktails. We are transmitting live from planet X31, 20 billion light years away from planet Earth. Science and Cocktails is an initiative taken by a bunch of people who believe that scientific research is worth sharing. Its purpose is to make people aware of scientific research and also of its uses through media, through art, through music, and even through the craft of cocktails. Tonight's teleportation will take you to a different universe, the one that cannot be seen with your own eyes, though may be felt. The universe of microscopic particles, of the quantum, of the small, the invisible universe. The android Troels C. Petersen, research lecturer at the Niels Bohr Institute, collaborator in different experiments at CERN, will outline a brief history of the universe, from the Big Bang to modern times, and will explain why this big machine, deep into the ground, able to collide particles at an incredible speed, can tell us a little bit about that part of the universe which we have absolutely no clue about. If you would like to take the scientist to the bar, get him drunk, and ask all the questions you would have liked to ask your own mother, you can just let him talk for a little bit. That which cannot be seen may be felt, and if so, it will be represented by the mind and hands of the artist Henrik Schulze, followed by an incredible session of questions and answers, while the most amazing cocktails are being prepared by Lars Erik Schmidt and his team. The Red Button Company, recently created, will perform on stage and show us some of the most amazing magic tricks that the world has ever seen. Through the code of Jelte Bestel-Muller, artist, musician, actor, and magician, we will hear some of the most astonishing sound escapes, built by means of algorithm techniques and generative design. End of transmission.
Okay, let's give an applause to Troels C. Petersen.
The universe is cold and dark and empty. Everything that was once there has decayed away, and only the very few stable relics are left. But every single particle that took part in the Big Bang knows what happened then. Even the vacuum knows the laws of physics and what went on. And by building giant accelerators to once again have that energy available, we can explore what went on in the Big Bang and how the universe and our world came to be the way it is. So go on a starry night out and look at the universe. And in fact, you'll find that everything you were taught in school is not correct, and that we know very little about the universe, and yet a little bit. So, a long time ago, this was people's perception of the universe. And already at that time, people wanted to know what's out there. What is the world we live in? And the imagination of the moon and the sun, and yet something beyond the stars. Now, with the exception of the Midwest in the US, we have moved on to a new picture of the world, which started with the Big Bang 13.75 billion years ago. And yes, we know the age with that precision. In fact, we also know how it's going to end. I'll hold on to that just a moment. Now, how do we know that? We know that from observing the universe. And we can do it with our eyes. This is a look not inwards, where you would see sort of a usual world map, but looking out. And here you have the center of our galaxy, the Milky Way, and the plane of it. And here you have a stripe, not taken in the visible light, but in the microwave band. The radiation that the universe emitted shortly after the Big Bang, and which is now very, very cold. 2.7 Kelvin, just above the absolute zero, so minus 270 degrees. And from the tiny variations in that pattern, we can say a lot about the universe. Now, in fact, that pattern is the very first picture taken of the universe. The universe was before very, very dense and hot, and atoms could not form because they would be kicked apart by the temperature. But after 380,000 years, it cooled below 4,000 degrees, and electrons and positrons combined into atoms. And in one go, the universe became transparent. And all the light that was caught in the haze from before was let go, and the greatest flash of our history in the universe took a picture of it. And that's what we're seeing there. It may not sound as much, but in fact from that we know the age of the universe. 13.75 billion years. And after about 2/3 of that running time, the sun and the earth comes about. So here's the history. We're about here. And we're about at a time where something funny is happening. And the reason why? It's all the things you weren't taught at school. So what we're trying is to start from this point nowadays and try to extrapolate back in time and see if we can understand the universe. The trouble is, in order to sort of run the movie backwards, we need to know the laws of nature that governs that epoch of the universe. Otherwise, we can't run the movie backwards. And unfortunately, the very interesting things happen beyond where we know. So that's our pursuit for the invisible universe. Here is a simulation of the universe as it expands, but it also grows into lumps. Now that may be hard to see in this movie, so let me do something magic you can do in simulations. Let's stop the expansion of the universe for a little while. And let's run it again, not expanding. And you see structures coming out. Each of these dots are galaxies. You see this structure? That's what it looks like in our simulations. Let's see what it looks like in reality. It has the same foamy structure. So we understand how we can run that movie. However, it only runs to fit that picture if we put in a lot of things that we can't see. Now, this is going to be one of the few graphs I'm going to show you. I'm going to show you a few. If you don't like them, just grab your cocktail, return in 30 seconds. Now, this on the x-axis is the amount of matter in the universe for a long time, and on the y-axis is the amount of energy in the universe. For a long time, everybody believed we lived in a universe that was made out of matter and no energy. Right there. However, 3 teams went to look at the universe in different ways. There were those who looked at the galaxy formation I just showed you, and they couldn't figure how the galaxies could form so quickly. I know that 13.7 billion years may sound like a lot of time, but it's not enough to form them if we just have the matter in the universe that we see. So they could say there has to be a lot of matter. The trouble is also that what we were observing at the time was only 5% of the matter needed to reach that point. And people also looked at the picture before, that first flash of the universe, and they could say, well, we're living in the orange area. And finally, people looked at distant supernova. And because the universe expands, they should be moving away from us. But they turned out to be moving away slower than we predicted. So the universe has been speeding up since then. And in fact, we live in a universe where only 5% of everything is made out of what you were taught about in school. The world is made of atoms. Does that ring a bell? Uh-huh. Well, locally it is. Your cocktail is. But if you look at the universe, it makes up a very, very small slice of it. So what's the rest? What is out there? Well, 2 components, dark matter and dark energy. Ooh. Now, why do we call it dark? That's because it does not shine. We do not see it in our telescopes. But also because it makes no sense in our minds. I'm going to talk mostly about dark matter because that's what makes most sense to us. The dark energy, it's not that it isn't important, but we just have no clue. And let me illustrate what no clue means. When you're a physicist and when you encounter something new, you say, all right, let me do a back of the envelope. You grab an old envelope and you sort of write, what if it was filled by the Higgs field? Something like that. Let's try that. How would that fit that amount? It doesn't fit within a factor 2. It doesn't fit within a factor 10. It doesn't fit within a factor 1,000. It doesn't fit within a factor billion. 10 to the 120th is the number you need. It's the most wrong we've ever been. Even the tax ministry have no numbers that size. So we have no clue what that is. Now, that doesn't mean that you shouldn't go be interested about it. A lot of people are. And if you have a good idea what the dark energy, this undilutable thing in our universe that makes it expand, what it's doing, what is doing this. If you have an idea, write it down, send it in, and who knows, in a few years, you might be having a fancy dinner in Stockholm. It's a sure ticket. But so far, we have no clue. Oh, yes. Now, for the dark matter, we have clues, and we're pretty sure. In fact, for the dark energy, we're not even sure, what it is, or if it's something that space in itself has. But for the dark matter, we have clues. In fact, we tried many things. The dark matter might be black holes. No, it's not, because when things fall into a black hole, they emit a lot of light, and we don't see it. Well, we see a few, but not enough to make up this. Could it be planets? No. Could it be dust? No. Could it be neutrinos? No. We tested all of that. Could it be a new type of particle which reacts very little and is a leftover from the Big Bang? Yes. You're giving it away. So that's what the hunt is on for. And we know that the dark matter is there. We've known it for a while because when you see galaxies rotate, you look at the outer stars, and a bit like, you know, some of these athletes throwing a hammer. Imagine that the athlete was invisible, but you could see the hammer, and you could see, you know, something weighing 20 kilos rotating around fast and then being thrown to hell. You imagine in your mind, all right, that's a Russian guy, he weighs 150 kilos, and then suddenly he becomes visible, and hey, he weighs 5 kilos. It's a baby. Something missing. What can hold on to stars rotating out there? People ask themselves. Well, it turns out we suspect very much the dark matter. Well, it could also be that Newton was wrong, right? That Newton's law does not work on very large scales. Well, we tested that as well. This is a composite picture containing 3 things. You look out at the sky and you see stars like that, nothing special. But then you ask Superman what he's seeing in the X-ray band. He's seeing this lump. That's because 2 galaxy clusters are colliding out there in the universe. And when they do that, they emit X-rays. That's because the atoms hitting the atoms emit X-rays. But we can also look in another way. We can look with our gravity telescopes. Now, what we do is, on Earth, we look out in the sky. There's a very distant galaxy emitting light. But because of something heavy in the middle, the light bends and we see 2 pictures of the same galaxy, there and there, but it's the same galaxy. And then we know how much is in between. And this game can be played with modern telescopes and fast computers. And therefore, we can see this picture. And it turns out that in this galaxy collision, most of it passed straight through and does not interact. And that's why we are sure it's not atoms. And it's not black holes, and it's not planets, and it's not dust, and it's not all of this. It passed through. And even, I'm a particle physicist, so I believe it's particles, but all of my colleagues in cosmology believe the same. And so the hunt is on for that. And in such a hunt, sometimes in order to answer the largest questions, you have to seek the answer on the smaller scales. Elementary particles. So let me sort of brush up your particle physics since last time. So the universe, no, our ordinary matter is made out of atoms. And the atoms are made out of a nucleus with electrons around. It's the electrons that decide the chemistry of the whole thing, so that's what binds your cocktail. But inside the nucleus are protons and neutrons. And they again consist of quarks held together by gluons. Now, there are 4 forces. There's gravity. And I'm not going to talk much about gravity because gravity is a very strange thing. It does not play well with the 3 other forces. What are they? Electromagnetism, which keeps the electrons around here. It's the strong nuclear force. That's what binds protons and neutrons, make nuclear reactors run, things like that. And then it's the weak force, which is also used in nuclear reactors and what makes the sun burn. Now these 3 forces we understand, and we can write them up like that. Don't try to memorize this, never mind. But this describes all the laws of nature outside gravity. Gravity does not want to play in the same scheme. Gravity is different. And just to tell you how extremely different it is, well, it tells something about the desperation in physicists when we try to invent 11 dimensions to sort of force gravity into this. Gravity works in this equation if there are 11 dimensions. All right, 11 dimensions? Oh, yeah. So people don't have a good clue of how to put gravity into that. We'll have to wait. Now, and down in the corner, we have sort of the periodic system of modern times. There are quarks. There are leptons. Leptons, that sounds like a strange word. The electron is a lepton. And then there are the forces, force carriers. It's in fact particles which are responsible for the forces. Now this equation may not seem like much, but put it into action, ask the theorists, and we can get some super precise predictions. For example, an electron is spinning, and so it's a good magnet. Well, it's a magnet. How much of a magnet? Well, let's ask the equation. You get a number out. You get 12 decimals out. And then you go to the experimentalist. Try to measure this. He measures it with 12 decimal precision, and they match. If you compare that to a golfer, that would be like standing here or in New York and hitting a golf hole in China. Hole in one. And so precise that it doesn't even roll over to the hole. No, it hits straight in without hitting the edge. Bang! When you have a theory that does that, you trust it. You trust it. And then it lets you down. Because it tells you that all the particles I just showed you before cannot have a mass. They cannot weigh anything. But we know from experiment that they pretty much all weigh something. So what do? Give up and drink cocktails? Well, you do that at first, but then you return. And you say, hey, are we going to throw all of this away? We worked 30 years to get this working? Hell no, we're going to add to it. We're going to add something called the Higgs mechanism. The Higgs mechanism gives mass to these particles. And so the Higgs is the last missing piece in our fine puzzle. It's not the only piece, because we don't know how many puzzles there are. But for now, it is the one piece we're missing. And so, what is this Higgs mechanism? It's a bit like a molasses. When particles move in it, they get hard to move, and so that's how they acquire mass. So if you're a massless particle and move through, well, you're not touched by it. You just move through and you keep moving at the speed of light. But if you're a heavy particle and you meet it, you get hard to move. And that's what mass is. And that's how the Higgs mechanism works. So all of this place is filled with a Higgs field. And the responsible particle is the Higgs particle. But we've never seen one. And while we haven't seen one, and this has been an outstanding problem for 45 years, theorists had come up with about 500 alternative theories. And so, doing experiments like we have to chase and see which of them are right and which are wrong. So we're chasing the Higgs particle, which sits sort of in the center and gives mass to all these particles, with the exception of these two, but never mind. Now, how do you do that? Well, you can produce new particles in a laboratory. It's a bit like changing money, and you all know how it works. You don't think so. But if you have energy, you can buy particles of a certain mass. It's like changing money. And the rate of change, speed of light squared. That's actually what Einstein's famous formula is. It's an exchange rate. If you have energy, you can buy a particle of a certain mass. Now, the more energy you have in collisions, so collisions is the only way we can have this much energy. The heavier particle you can buy. And the heavier particle, the less likely they are to produce. We can't decide what we change, which currency we get back. Mostly, nature will give us cheap Polish zloty, and only few times British pounds. Now, and this turns out to be a technical difficulty I'll show you in a moment. So what we do is that we collide particles. Now, it sounds strange. Why would you just smash things together? But imagine a world built of clocks, mechanical clocks that wake you in the morning with two bells on top. If they were so small that you couldn't see them with your eye, but you had a suspicion the world was built of those, what would you do? Well, you could accelerate them, a lot of them, and once in a while, two would hit each other. And if you had a detector around, you could see them fly out. And how often that happens has to do with the size of the clock. So you can sort of guess the size of the clock. But if you don't want to know the size of the clock, you want to know everything, or at least we do. So we collide them harder, and at some point the bells come flying off, and you don't see 2 things flying off, you see 6 things. And then you say, the world is made of clocks, they have this size, and they are made of 2 bells and 1 central part. Are we satisfied then? No. We collide them harder. And then all the bits and pieces inside these clocks will come flying out in your detector, and by doing it again and again and again, you will slowly understand what's inside the clock and what makes it tick. But we don't live in a mechanical world. We live in a quantum mechanical world. So out of clocks, you can have cars, airplanes, whatever, come out. You just exchange energy for matter. Now, that all sounds simple. It looks more like this mess, unfortunately. And as I said, it's rare that you get the things you want. Mostly, you get the light particles. Sometimes you get a B quark 1 in 300. It's like being born on Christmas Eve. It happens. Sometimes, but only 1 in 1,000,000 to 10 million, you get a W or Z particle. It's like winning the lottery on 1 ticket. And only 1 in 1,000,000,000 do we get a top quark. That's like winning on 1 ticket and being born on Christmas Eve. But to get a Higgs particle, you need 10,000 billion collisions. And that's to get 1. We want a lot. So what do? Well, we face the challenge. We think of an experiment that can do this. And so it begins. Now, here is CERN's Large Hadron Collider. Buried underground outside Geneva. This is your average 500,000 inhabitant city. Here's an international airport to sort of get the scale. Lac Le Mans, Mont Blanc, and here it is. So, and around this are 4 experiments. I work on the Atlas experiment. And people have been working on this for years. No, decades. It started in 1984 with the first meeting, how do we face this challenge? And by now, it's ready. And I admittedly have stolen a bike and taken a 4-kilometer ride down this way. And believe me, it continues this way. All the way around. Now, it looks easy. You might think, well, do like IKEA, right? You get 60,000 of those, 80,000 of those, right? And instead of creating a black hole, you call IKEA, right? And then you just collect them and fill in protons, and there's your fancy dinner in Stockholm. There we go. No, it ain't that easy. This is a zoom in of some of the superconducting wires. They're about 1 millimeter across. And they look like copper, right? But inside each of these are 6,000 strings of niobium titanium superconductors. I asked one of the accelerator physicists, who can make this? Well, he said there are 10 companies in the world. So I thought, all right, it must be cool to be the company that got the order from CERN to build all of this. He said, no, they all liked it because we hired 9 of them for 6 years to do nothing but that. And the last company, of course, got all the other orders. So that's put together in the LHC accelerator. So pay respect. I'll take a prize for that. Cheers. Whoa, it doesn't fit with the microphone. So the ring is underground, and there's a whole accelerator complex to send protons around and collide them in 4 places. Now, building such a thing, you need to do some digging. Here's the beginning of the digging. You dig 100 meters down, and then you send a lot of material up, and you have bulldozers and running around there and engineers. And slowly you get to cover the walls and do all the electrical installations and so on. Here's a small movie of a random week in building it. Notice here is the LHC accelerator. Here the beam comes in, And on the underground here, you have to build something because it turns out that the signals from the detector need to go to computers. But computers can't take the radiation there, so they have to be shielded. But because of the limitation of the speed of light, you can't send the signals far because you need to take fast decisions. So they're buried underground here with fast electronics that can take a decision for you quickly. The cave being built underground is like a bubble in water. Of course, Earth is not as liquid as water, but it's liquid enough that the cave moves. It moves up 1 millimeter a year. Now, it was estimated that it would take 6 years to build the cave. So it was built 6 millimeters under where you needed it. By the time the experiment was done, the accelerator could just point downwards and make this work. And while we're running now, it still goes up. It can go 12 millimeters where the accelerator can reach it. And so in 12 years, there will be adjustments. I'll show you the size in a moment. So how to build a detector? Well, think a bit like Leonardo, and you think of this thing. Here's the Atlas detector. And this is your average size physicist. It's not an Italian, it's a real size. So it's 44 meters long, it's 22 meters across. So the round tower is thin like the red and not as long. And it's filled to the brim with specially designed electronics up to the task of looking for these trillions of collisions. Now, this is what it looked like in 2003. This is what it looked like in November 2005. You see people working here. This is moving that central part into the piece. And I've seen professors cry when the detectors they worked on for 15 years finally was lowered into the hall and installed. Welcome to one end of the Atlas detector. This is where the beam comes in. This is how you assemble it. And here's a short sketch of how you see particles. If this is transversely, then if you collide protons here, coming from you and coming from the other side, well, what happens if you make an electron? An electron will come flying out, and then it will stop here, and it will leave a track in the inner part. So you see a track and a stop particle here. That's an electron. A photon is not charged, so it doesn't leave a track, but it does the same here. A proton continues through, and it leaves a track because it's charged, but it stops out here. A neutron doesn't leave a track, but stops out here. A muon, what is a muon? Well, it's a heavier brother of the electron. But because it's heavier, it goes all the way through. So we build detectors out here, and when we see things out here, it's probably a muon. And then there's the neutrino. Neutrinos do not interact very much. In fact, very little. The sun produces them at all times, and the universe did for a long time. And every second, there's 1 billion neutrinos passing through your fingernail. And most likely, none of them passing through you will ever react with you. They're very ghostly. Our suspicion is that the dark matter in the universe is equally ghostly. It only reacts with a weak force, and that makes it hard to see, if not invisible. At least for now. So that's what we do. We look at this, and here's a zoom in on the tracking part. So what happens, how we see particles, is that it passes through a little piece of silicon here with a voltage across, and that gives a signal. So we hear bing, 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 bing. And so looking at that, we can create, say, probably a particle ran there. In fact, we put the whole thing in a magnetic field so we can see how much it bends, how much energy it had on it. And also, the Niels Bohr took part in building this detector, and we filled it also with the gas called xenon. Xenon has the smart ability that when electrons go through it, they don't say bing, they say bing. So we can see if it's an electron or not. Now that's very interesting, because when you collide protons, there are no electrons inside. So if you see an electron flying out, then something happened in that collision, which is worthwhile to consider further. Now, And then the unexpected. Meanwhile, people invent these electrical lamps for painters with xenon in, and that made the price of xenon go up by a factor 12. And then you have to creep back to your funding agency and apply for more money. We need more money. We need xenon. Can't you do with something else? Sorry. And then you fix your pipes so that they don't leak. And then it's ready to take data. There are 100 million things in this detector that can say, bing, I got hit. And they can do so 40 million times a second. And we typically run 15 to 20 million seconds a year. Now, the amount of data in that is the equivalent of all telephone and network cables coming at you from the entire world. And we have to take a fast decision because we can't save that on tape. We can only save 1 in a million. And we have to take the right one because we don't want to throw that one Higgs particle away. So fast electronics and smart computer programs does this. And when we've thrown away a factor 1 million, we save 5 to 10,000 terabytes a year. That's the typical size. And we use about 100,000 computers in parallel to run over that data. Yes, we spend a lot of time in front of our computers playing with them. And what do we see? Well, here's a simulation. In fact, no, this is real data. This is from a real collision. And what you see is 2 muons, because they go all the way through, and then you see a lot of other stuff. All this nasty stuff that makes it pretty hard to see what's going on. Now, that's the price of trying to get all these collisions in. We collide things very fast. And so not only do we get one collision creating the Z, but we get 10, 20, 40 next year, collisions on top of each other. And it's finding a needle in a haystack. But that's the price we have to pay to get a lot of collisions so that we can get a few Higgs particles. And there's the chase. And we don't chase just the Higgs particles. We chase black holes as well. And when journalists hear about black holes being produced at CERN, they go nuts. Are you going to destroy the world? No, we're not. How do you know? And then you give them a story, but that was too long. It actually made the front page of New York Times. So how to observe a Higgs? Well, here's actually a candidate. One of the things the Higgs could decay to is 2 Z particles, and they would each decay to 2 muons. So you would see 4 muons. Now, that could have been a Higgs particle. By now we know it ain't. The Higgs, another graph. Now it's technical. Now let's say the Higgs weighs 125 GeV. That's the energy you get if you take a particle and accelerate it over 125 billion volts. Yeah, you take your average battery and then you just take a ton of them, billions, and then you can do it. Don't do this at home. Now, it decays mostly to B quarks, but we can't see them because we've got tons of B quarks. But what we can see the best are Z's and gammas. And now I'll show you the Higgs evidence, why we've been discussing things. Now, all of this up here is where we know the Higgs isn't. It's below 150. We know that. And suddenly 3 events have exactly the same mass. Now that's suspicious. The Higgs doesn't only decay to Z's, it also decays to other things. So let's consider other things. What about photons? Well, there's a lot of crap. But there is a bump also there. It's not large, but it's there. So have we found the Higgs? Well, the chance of this being just noise is 1 to 500, 1 to 1,000. Would I make a 50-50 bet that we've seen something? Oh yeah. Would I put my head, my entire research career, and say we found it? Probably not. That's why we haven't claimed it. That's not enough for a discovery. And so, we can't claim discovery. We're waiting for this year's data. The LHC will 4-double the amount of data that we're going to take, that we have already. And so, by Christmas next year, we will know if the Higgs exists or not. And if it exists, we we will have found it and have evidence. That was a promise. Otherwise, I'll buy around here. And then finally, for a few relations to the real world. What has all of this got to do with the real world? Well, World Wide Web was invented at CERN. No, it's not the American military. They invented emails. But World Wide Web, HTML, is created by, now, Sir Tim Berners-Lee, who sat in an office and thought, how do we coordinate technicians and engineers with the crazy physicists and some of the theoreticians dreaming up 11 dimensions and whatnot? How do we coordinate that between Europeans, Asians, Americans? Well, Sir Tim Berners-Lee had an idea, so he ran to his boss, and imagine explaining what the World Wide Web is when it doesn't exist. I have this idea, an associative way of dealing with information. Where? On your computer. How do you associate? Well, you click on it. Can you write that up? Sure he could. Tim Berners-Lee said, information management, a proposal. And so he said, this is a proposal. You can see it with Inquire. That was the first web browser. He just made it himself. There were 2 offices, by the way. So he drilled a hole and put a wire between the 2. And so it was the server room on one side and he was surfing on the other side. That was the World Wide Web. In fact, at CERN, you can still see the server. He had to tell the cleaning ladies not to shut it off because it was a server. They didn't know what that was, but they didn't shut it off. And so with Inquire, you could see this proposal, and you could have documents, and you could have, CERN could have documents, and a proposal could be part of the CERN documents, and at least that's what his boss said. He said, vague, but exciting. He actually wrote that on top of it. And so he told Tim Berners-Lee, you know what, go play with that for 3 months, come back, show me what you got, and we'll look at it. And then he thought, that looks good, assigned a few more postdocs, a few students to it, keep playing. And next thing you know, you got something quite valuable. Yes, we're spending billions, but I think Google could run us if they really wanted to. And in 1999, CERN signed a document saying that we will never charge anything for the World Wide Web and HTML. And that's what drives businesses, because you don't want, as a business, to invest in something which could suddenly cost you a lot of money. But if you know that it's signed away and for free, there you go. And CERN doesn't only do this. CERN has a lot of other contributions, especially in medical science, but also just in technology for building stuff. Whenever you build something large, you come across new things that you want to do. There are also things you want to avoid. This is a matrix printing from before you had all these fancy plots. And it's from an experiment called SETI. And in 1977, Dr. Jerry thought that he saw signal. They're talking to us. 0s, 1s, 2, 3, 4 is noise. 6 and 7 is interesting. But this, he said, wow, signal. But it's not. And we need to avoid doing the same thing for the Higgs particle. That's why we haven't said, wow, signal. And we need, for the Higgs particle, all right, we're having fun about it, perhaps we'll find out afterwards. But in medical science, it's quite important that you don't say, wow, tumor, or wow, no tumor, and making a wrong decision. And so the statistical tools for analyzing data and making sure that products work using cross-checks and control channels, things like that, we're developing as well. I know that sounds boring, but it's a contribution. And so with that in our back, we don't focus on that. We are Higgs hunting, and this year we are on. And so, to conclude, the Higgs particle is one of the main challenges of the 21st century. And the LHC experiments and its experiments are running fantastically well. We got 5 times as much data as we had dreamed about this year, and next year they promised 5 times more. So the hunt for the Higgs particle and dark matter and extra dimensions are in full swing. And it's many days and nights that will be used, and many wages that will be lost and won, many winters of despair and many springs of hope. And we don't do it because it has practical results. Thank you very much.
Okay. I think that's maybe a bit too much, you know? Huh? A little bit? Before we can take Troels and have fun with him at the bar, we have time for 3 questions. So, if someone would like to ask a question.
Is there a reason why it's built underground? Yes,
yes. It's so large that, well, Earth is not flat enough, so we would have to raise it. And also, unfortunately, just around the detector, it's not good to be when it's running. It's a bit radioactive. So underground is a good place to build it. And also, we need things stable. And to illustrate that, in the previous accelerator there, they were seeing some results that they could measure very accurately. They tried to say, well, let's plot the result every day. And then it turned out that that the result was changing monthly, swinging. And people said, it's the women on the experiment, that's why. But it turned out that it was the moon, and in the same way as you have tidal water, you have tidal earth. It's just a very small effect, so you don't see it. But it changed the 27-kilometer accelerator by 1 millimeter. And that could be seen. And then they started thinking, okay, what else is affecting our accelerator? And, you know, what do things change like time? And there was a change every 4 hours, but only during daytime. Coffee break? It's not a bad idea. You know, breakfast, lunch, dinner, or something like that. No, it turns out that that's the running schedule for the TGV going from Geneva to Paris. And it sends electricity into the ground, and that's a coil, and there you go. And it turned out at the end that you could tell how much it had been raining in the Jura Mountain, what the sea level was in the Geneva Lake.
So it has practical...
So it has practical purposes. And that's why we build it underground, to have as stable an environment as possible.
Any other question?
What would it mean if you find the Higgs particle? Will you be able to manipulate gravity, or go back to the Big Bang, or create real black holes and scare the New York Times?
I'd love to do that, or at least some of the journalists there. No, the Higgs particle in itself doesn't have any practical purposes, but it would be a great triumph for our minds to sit 40 years ago and say, I think, looking at the world, that there should be such a particle. It may take 50 years to find it, but it will weigh this and that much, it will decay this and that way, and it will be responsible. And the formula I showed you, we will have even greater confidence in. It will describe the world, and we will understand the world, if we get that last puzzle. And then, not yet, right, there was dark matter and some other problems. We've got plenty to do.
The third and final question goes to...
We are actually building an accelerator at Lund in 2020. What do you think it will mean for your... Then you have at least 8 more years, but what do you think that will mean?
The European Spallation Source, as it's called, is an accelerator which is, I'm sorry to say, by our standards, small. It's about a factor 10,000 to 100,000 lower in energy. So it's used for looking at large molecules that is used in medical and other material sciences to improve on that. So in fact, regarding application, it's going to have a lot more applications, to be frank. However, we're looking into building something which is not for application. You could also accelerate particles and shoot them into a wall. And that stops everything except the neutrinos. And it turns out that the neutrinos are very, very interesting, because the matter we see in the world today, there's no antimatter. And that's very strange. We thought that the answer was to be found in the quarks. There is a difference in the quarks between matter and antimatter, but way too little. But the neutrinos might hold a big difference. and have made all the matter that even our cocktails is made of. Our cocktails knows what went on early in the Big Bang. Now we have to find out. So it could do that, but mostly for applies. All right?
Okay. Okay, that's it. Let's give maybe another applause.
Something here? I should be saying something. Hello. Hi. Well, good evening. You're very smart. I've been sitting out here listening to you, you know, very clever, big brain, huh? You don't drink it all away, I can hear. Wow, I like it. Maybe we meet later in the bar, huh? I'm Lena.
Hi, Lena.
Lena, hi, good evening, everybody. I just passed by. Hi. You know, yes, I do, because I really like this place, Byens Lys. It's like amazing. I came here once in a while, and then I do some cabaret here with a lot of my friends, and people are just so very friendly. And then I pass by, and then my friend, the mad professor, he's up there somewhere. He says, come by, say hello. So I decide to. So, hi. Or maybe I come out here in the spotlight. Yes, thank you. Wow. I like it. I feel home here. Yes, maybe I come and live here with you. This one small table, yes. Because actually, one reason why I'm here is because I come to pick up artists, you know, so we can travel around and make some shows and meet different artists and all of this. And so the last time I came here to this beautiful town, Christiania, we bring with us this troupe of ours, a couple, a really amazing couple, and now we pass by here again, and then we decided to that they should make a show here, and I should go to the bar and drink some cocktails, and because that's what I do. So they're the performers this night, and they have formed this little company without me, called the Red Bottom Company. Yeah, it's really disturbing, you know, you travel around with this group and you feel like they're your family, and then they end up staying and forming a company and not inviting me. So I come myself. Yes, so the couple we are going to see, they're really nice people, unless they stab you in the back. But they're called the Red Bottom Company, and yes, it's Katinka and Fedora, and they come here to perform for you and all of you guys. I see you in the bar. I hear they have some very nice vodka here. Yes? Okay, thank you. Enjoy. Bye-bye. Nice.
Isn't it lovely, darling? And all this beautiful water. Look. Oh. Now look what you've done. Oh. Where are you going, darling? There's nowhere to go on this boat.
Really, Katinka, I had no way to feel like this for me. I feel like this for you for a very long time. Oh, darling, let's sail the oceans and the seven seas together for always. Kiss me. What the hell? Oh, oh. 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 Ah, yes. Oh. Oh. Stop! It's on your left. No, the other left. You lost 17 good men. Went to 17 great fields. Where the lights are on all night. What is that boat without you now? Need I remind you that boat once more? No use to remember, that's for sure. Yes, anybody's life is only half complete if you haven't walked again on this street. You lost 17 good men. Went through 17 great fields. Where the lights are on all night.
What is that boat without you now?
Well, a while ago, they changed its name. Things are turning into a whole new game. No matter where you go to find what must be found, I bet you that carrot boat is all around. You lost 17 good men. Not sure I get now. Went through 17 great fields. Where the lights are on all night. What is that but without you now? Oh, sure you can get now. Men. That's right, went to 17 great fields. That's right, where the lights are on all night. That's right, what is that without you now? I was your Kayatna. Where is your black handgun?
What is that boat without you now?
I was your Kayatna.
We'll have a 15 minutes break. You can ask Troels whatever questions you would like. And after that, Jelte Bestel-Moller is going to perform his sound works, which are based on algorithm techniques and generative design. It's really interesting, so stay.